My name is James Strassburg. I'm acting as Technical Fellow and Chief Software Architect at Direct Supply, and I will let Jack introduce himself.
My name is Jack Schlederer. I'm acting as I am a senior software engineer at Direct Supply.
So some of the stuff we're going to be talking about today are our re-architecture from a replication model into SolrCloud. Along the same time, we moved into AWS. We're also going to be talking about why we're running Solr in containers on immutable servers, treating them as stateless, our use of chaos engineering, and some of the issues that we dealt with along the way. Direct Supply, where I've been working now for 20 years this month, is a supplier to the long-term care industry. We work with nursing home chains and assisted living facilities and provide various services for them, e-commerce procurement, to catalog management, spend management, interior design services, building maintenance, and so on. So we started our migration into the AWS public cloud about 2 years ago. And as part of that, I was involved in helping put together our cloud vision and strategy for Direct Supply. We wanted to get away from the traditional infrastructure versus software model and get into more DevOps mentality. So some of our facets of our strategy included things like immutable servers. Once we have a server running, we don't want to do anything to it. If we end up needing to replace the software or patch those instances, we build new images, destroy what was running, and the new stuff comes up from the new images. We moved towards infrastructure as code. We're going to be covering a little bit about what we did with HashiCorp's Terraform tool in this talk for SolrCloud specifically. But traditionally, our infrastructure teams were not using much automation to develop systems. So now we're a DevOps model. We're doing almost exclusively infrastructure as code. Along the lines of that, automated deployments. We wanted systems to be secure by default. And as part of this, we wanted to get towards providing a platform as a service towards our engineering teams. So the idea of that being, if we have some reusable piece of infrastructure code that a team can use, we're hoping that when they stand up whatever resources run in that module, we'll say, they are secure by default and they meet all of our best practices. So this is going to be more of a systems engineering talk than an internals of Solr talk. We'll talk about how we look at systems engineering and then how we applied some of those techniques towards running SolrCloud inside of AWS. I think this is really important because data is everywhere. You hear that, this is a data-driven economy, and systems like these are almost to be considered the new means of production. So if we get really good at building and running these systems, we're effectively building the machines for the future. Click. So I wanted to talk a little bit about how we're using Solr inside of Direct Supply to start with, to kind of frame the rest of the talk. We have an e-commerce application that you see here, and we're doing various things with Solr behind this application. We're using it for a traditional product search, and right now our products collection has approximately 12 million documents in it. We're using it for order history search, because they're searching both the orders themselves and the lines on those orders. Our order history collection has around 100 million documents. We're searching invoices. We have around 50 million invoice documents that we're searching. And of course, we're using things like filtering and facets for our categories. You can see the little numbers on the screen. And we're doing some autocomplete. So our e-commerce application is using Solr pretty heavily, although maybe not quite as big a scale as some of you are using.
Real quick.
Yeah.
Other than just Solr, what else is involved in the e-commerce app that is kind of, what other pieces are touching that?
The main database behind it is SQL Server. So it's a .NET web application backed by SQL Server. Services have been carved off over the years.
We have a few internal services that make near real-time updates to products and orders and invoices and all that.
Sure.
So our ingestion is quite complicated, and we'll talk about one of the challenges we have with our product index later. But at this point, I'm going to turn it over to Jack so he can talk about how we started with Solr and how we evolved into what we have now.
Thank you. So we've been running Solr. We started at version 4 back in 2014, right? Yeah, 2014. And then we used our original Solr cluster was not really a cluster at all and was really just a master-slave configuration. So what's often referred to as the Solr legacy configuration, which is we have one master and we have multiple slaves, where the master takes all the updates, does all the indexing, and the replica or the slaves handle all the queries. And there's a load balancer in the middle to determine, is this an update or is this a query, and then it routes it to the right node. There were many problems with that original architecture, namely being it doesn't scale all that well. And really the only way to scale up your indexing capacity is to make that master node bigger. And the only way to increase your query capacity was to add more slaves. So there was a little bit of wiggle room to scale out, but it was primarily scaling up. So we decided to move to, 2 years ago, or what was it? Just a few months ago, right?
Yeah, a year ago.
Just a year ago, we decided to move to SolrCloud, give us an opportunity to re-architect that cluster while we move it into AWS. So that got us, well, right, opportunity to re-architect, gets us index charting, gets us 3 replicas instead of n replicas per SolrCloud replicas instead of slaves. Scale out, auto healing, and we got the opportunity to treat servers as stateless. So as we were hinting at before we started this talk, we're trying to get into more of that mode of let's start operating stateless servers. Where we don't have to really log on to them to do anything, and then we can just terminate them if they ever start being problematic. So this is, as a whole, what our cluster looks like in AWS. So we're using an application load balancer to route requests to an ECS cluster, an Elastic Container Service cluster, out in AWS. So we're running Solr and ZooKeeper all in Docker containers on EC2 instances. And then we're also using a Lambda to trigger a backup every night of all of our collections. And then we're using the file gateway to go to S3 for the backups. So our backups, when they get triggered, will get sent to a file gateway, and then they will then be persisted to S3 for durability.
Don't try to take that all in right now. We're going to talk about the pieces, piece by piece.
Right. All right, so one of the main things I wanted to cover here was using containers instead of running, Solr right on an AMI, right on an EC2 instance. And this gets us really a couple of things. So number one, it's much, much faster to iterate because tearing down or building a container in AWS or building it wherever, building a container image is much, much faster than building an AMI. Probably, we're talking about 10 minutes versus an hour and a half to 2 hours to build an AMI. Scaling is faster because we already have a fleet of EC2 instances out. So whenever we want to place a new Docker container, we just say, hey, go place the container. And it does it in a matter of seconds rather than waiting for new EC2 instances to spin up with our AMI and wait for Solr to start on all that. We originally targeted Fargate, so basically serverless containers. We decided against that route. We ran into a roadblock, which we'll tackle in a little bit. They can be placed anywhere, so EC2 instances, obviously using ECS, but it's also great for developer workflows. So you just run Docker on your computer. You can pull down our container image, run it, and then that has all the config sets, collections, all that stuff built in. So surely you all know what ZooKeeper is. It gets us. What was that?
Oh, I'm sorry.
Oh, yeah, you're good. So, storage of configuration, cluster coordination, and leader election. We all know what ZooKeeper is, the main cluster coordinator within a SolrCloud environment. So let's talk a little bit about how we operate our ZooKeeper ensemble in ECS. So we actually use we use a ZooKeeper ensemble of 3, which gets us the ability to lose one ZooKeeper and still keep taking queries, so our cluster doesn't go hard down if we lose one ZooKeeper node. The way we instrument that is through 3 separate ECS services. So each ZooKeeper lives in its own single task Elastic Container Service. And the reason we do that is so that we can use Route 53 service discovery. So Route 53, which is Amazon's DNS service, has a subservice called service discovery. So basically, it will automatically assign a SRV record to each ZooKeeper task with a TTL of 10. So it's never more than 10 seconds, or that DNS entry is never more than 10 seconds old. So that means that for every Solr server, we can just reference the ZooKeeper servers like this. We just give it the static DNS name. Those will never change, so it'll always know what ZooKeepers to talk to. Now let's talk about how we do, a little bit more about how we do SolrCloud in ECS. And it's very similar, except it's only one service. So we say we want 15 tasks. And we can decide how much memory to provision to them, how much CPU to provision to them, and then it will automatically place those on our fleet of EC2 instances, or spin up more EC2 instances if we're under-provisioned. So ultimately, that cluster altogether is culminated in this one Terraform module. So do we have anyone here who uses Terraform for a couple? Okay.
Oh, yeah.
So Terraform is just a, as he hinted at before, it's just a infrastructure as code tool. So you declare all your resources in code, all your AWS resources in code, and then you just use a CLI, Terraform apply, and it goes ahead and spins them up. And it also keeps track of state, making sure that it knows what it's already deployed, so it doesn't have to deploy them again on subsequent applies and subsequent updates. So ultimately, this gives us a really, really nice view of what we have running in our SolrCloud environment. And this is all configurable. So, you know, if you need to add more heap, you need to add, you need to provision more CPU, you need to provision more memory, you can all just write these all, or you can change these all, just run Terraform apply, and it'll go do its thing and update it. So a couple things I wanted to point out here. That file, so we have a file share ARN. So as I hinted at before, that is in charge of, or that is the backing storage for backups. So when we trigger backups, they will be written to that storage gateway, which will then be, and that data will then be persisted to S3, and that gets mounted on every single one of our EC2 containers so that all the Solr nodes share that shared file system. Another one that we have built in here that I think is really cool is PagerDuty. So here you guys use PagerDuty for monitoring infrastructure, couple. So PagerDuty is basically just infrastructure, or basically just alerting and monitoring for infrastructure. And we have it built right into the cluster. So you just give it an endpoint, and then whenever a certain set of conditions are met, it'll fire an alert to that, and someone in our SRE department will get an email.
Real quick, so this might just be a Terraform question about the infrastructure, but if you make a change to this, it's persistent across newly created modules, or it actually goes back and edits the modules that are already up and running?
So this only encapsulates a single cluster.
Sure.
So if we want more clusters, we'll have to replicate that.
Okay.
But if you make that one change to one of those lines, that will only be applied to that one cluster.
But it's applied to that cluster, to all the members of that cluster, pretty much instantly.
Correct, yeah.
Okay.
One thing with our use of modules that you can't see here is when we change the module itself. So for anyone that hasn't used Terraform, any collection of Terraform files can be used as a module, and you can reference them on the file system or right out of Git, which is what we're doing. And one thing we can do is we can reference a branch inside of Git. So we use major revision branches inside of Git for breaking changes to our modules. Okay. So what you would see here is SolrCloud module ref v1 for the v1 branch. And then when we break that, if we know it's a breaking change, we'll go to v2. If it's a backwards compatible change, we'll commit that and merge that into v1. So that on subsequent applies, they might get, you know, feature additions or bug fixes.
So that source path to module up there, that can either be a relative path or an absolute path on a file system, but it can also be a Git link or some source control link that it'll just go, and if it has access to, you know, it's properly authenticated, it can just go and download that from Git.
Okay.
And this is a big part of our strategy of providing a platform to our development teams. We're doing stuff like this for everything we're deploying, not just Solr. So even the ECS cluster within this module that we're deploying is another module that's usable by other teams.
Yeah. So let's talk about a couple of things that are built in here, or a couple of features that we take advantage of to get added resilience. So in Solar, when you go to create a collection, you can set the auto add replicas flag to true, which means that it will build in an auto scaling trigger into your cluster such that if you were to ever lose a replica or lose a node, whenever a new node gets added, it will automatically recreate that replica. So auto add replicas equals true. And then we also use rule-based replica placement to make sure that when we create a collection or create new replicas, we don't want the same replica of any shard being co-located on the same node, because we don't want to lose two replicas if one node goes down. So we use rule-based replica placement to make sure that this makes sense, or that this is enforced. Less than two of the replicas on any node. Another one that we added recently, and we just scaled up for this, is we're making sure that some of our hardest hitting and hardest queried collections live by themselves on a node. So that's another thing that you can do with rule-based replica placement. And that's so new that we haven't put it on the slide yet. So we're using auto-scaling triggers as well. So like I said, that auto-add replicas sets implicitly a trigger in SolrCloud to say, if a node gets lost or a node gets added, make sure you take the corrective actions to add the replicas back. Node added, node lost. So we use AWS ECS to monitor container health. So ECS, along with the built-in health check on the application load balancer, makes sure that any containers that are behaving poorly get swiftly terminated and replaced with a new node. So ECS will monitor containers, and then the ALB monitors the instances. I'm going to pass it back over to Jim because we're going to talk about our reindex process, how we get data in, how we even get data into the thing in the first place.
Cool. All right, so one of the problems we had to solve when we moved to SolrCloud was that we're still doing a nightly reindex of our products collection, and this is something we've tried to get away from. But we have a very complicated ingestion process where different suppliers give us, catalogs of products in different ways. So for a lot of the updates that happen throughout the day, we do use near real-time updates directly to the SolrCloud collection, but we haven't gotten away from the nightly reindex. So our original process was that we would disable replication, clean the collection, index it, and then if that was successful with retries baked in, should it fail for some reason, we then enabled replication, and this prevented us from ever serving a partial index as search results. The problem was when we went to SolrCloud, we no longer had replication to disable. Queries that were going to the cluster were going to get whatever that collection was returning at the point that the query was made, so we could no longer do the clean and hope to not serve a partial collection to customers. So the solution that we came up with was to make use of aliases, which we discovered as we were doing this work. And what an alias is a pointer to a collection, if you've not used them before. So we have, let's say our web app was accessing the products collection with the name products collection. We then made that an alias inside of SolrCloud. And what our reindex process looks like now is that when we go to index on the nightly reindex job, we create a brand new collection that has like a date timestamp as part of the collection name. We reindex it, and then when it's done and successful, we simply update the alias to point to the new collection, and then we can delete the old collection. And we've had very good success with this because in the middle of the day, we can add a new collection. We've even done some stuff where just last week, we ended up sharding our products collection for the first time, and we weren't sure how that was gonna, like we had all the testing we could do in QA, but it's one of those things that makes you nervous, and we wanted the ability to very quickly flip back. So what we did is when we created the new sharded collection for products in our production environment, we left our old collection in place with the idea that should something go haywire, we just make one API update and we're pointed back at the old collection. Maybe the data's a little bit stale, but we don't have to wait. I think our full reindex takes like 3 hours. So it's still doable within a night, and we're still moving to get away from it, but this really helped us in the short term move to SolrCloud.
Real quick, how big is your index as far as like file size?
Products
about 10 to 12 gigs.
Okay. And you said it was about 100 million objects or 100 billion?
Products is about 12 million documents. Yeah. We sharded. We didn't think that was enough to shard, so we didn't shard it originally, but we have a very complicated document structure of which catalogs evolved into be something different than it was originally. So the complicated queries actually, when we sharded, cut our query times almost in half, our queue times.
What are your queue times now?
20.
Okay, and
They were 40, 45, yeah. So not bad, but I was actually kind of surprised by that. I thought they would get a little bit slower, but we don't go so deep into the internals.
Right.
Another thing that we did as part of developing the SolrCloud was to install chaos engineering into the process. And this is something that's very new for direct supply. Netflix is famous for having the chaos monkey that kills things randomly, and that's what we've installed initially. We're not doing it in production yet. We are doing it only in up to our QA environment. But what we do is we have an AWS Lambda function that runs on a schedule, and every hour it runs, and we configure it with the likelihood of killing a random task or instance in the cluster. So every hour it's going to run, and then based on, if we said like 20% chance, it's going to kill an instance or a task.
Now,
Yes?
Sorry, so you have 2 shards and how many replicas?
For products,
Yeah.
5 replicas right now. Yeah. We grew that from originally 3, and that helped us with some.
So
Query
10
throughput.
nodes, basically 10 nodes and 2 times 5.
Yeah.
Well, we've got more nodes for the other collections that are on there, like order history and invoice, but yeah.
For one, I mean, so you're killing one at one.
Yep.
10th or-
Yep, so that Lambda runs every hour, and the testing that we did with this actually led to 2 JIRAs getting opened. One of them was the ZooKeeper had a JIRA open for itself, and the version the bug that we were hitting that was patched wasn't in Solr yet, so there was a JIRA open for that. And then there was another one related to auto-scaling, moving core properties around. I think that one might still be open. But it was kind of interesting that this chaos testing led to these 2 JIRAs being opened up. And we also discovered a whole bunch of stuff inside of our process that wasn't what we expected. So this has now become part of our system productionization. When we build a new system and productionize it inside of AWS, we're setting up chaos engineering almost from the outset.
Specifically distributed systems.
Right, for distributed systems. It did cause one issue that I'll talk about in a little bit, though. Backup and restore. So as we talked about a few times, we're treating our individual servers as stateless, where we're not preserving the disk in any way. So if we lose one node, we're going to lose, let's say, one replica of our products collection. And to get that back, we're relying on the ability for the auto-scaling triggers to place a new replica somewhere else. But there is the case where, should we somehow lose all of the replicas, what do we do? Because now we don't have the disk anywhere. And in our use case, we were looking for a low RTO. If you're familiar with RTO and RPO, that's recovery time objective, and RPO is recovery point objective. So if you're going to recover in like a DR type scenario or a recovery scenario, the time is how long it takes you to recover, and the point is how far you want to go back. And for us, the point objective was 1 day. We said we can live with yesterday's data as long as we can get it running fast. Some other organizations may have different requirements, but for us, this worked really well. And we also wanted to land our backups into S3 for durable storage. We get, I think, 11 nines of durability by having those backups in S3. And the way we end up recovering, if we did have to recover, which we did have to do a couple of times, it's actually very fast. 12 gigs comes back in not a lot of time.
About a minute.
Yeah. So the architecture of that, we have another Lambda function that's our backup trigger that runs once per day to get us our daily backup. That's our recovery point objective. And what that does is it uses the Solr API to make a request to ask for a backup. And the configuration of that is set to look at the file system to a mounted path. And we're making use of an AWS service called the File Gateway or Storage Gateway. And what Storage Gateway does is it's backed by S3, but it keeps a cache volume and exposes an NFS share. So you can mount an NFS share on each of your Solr nodes, which is what we do inside of ECS. And that gives us the shared file system that's required by the backup API. And when we write it, we're writing to what looks like an NFS share, but the data then gets trickled back to S3. So that's worked really well for us. We're using that in several other areas too. A coworker of ours spoke last year at reInvent on our use of that for SQL Server backups.
Just real quick.
Yep.
So when you're talking about data recovery on Solr, you call that API and it pretty much just sends out just the index as a flat file, and you just get the indexes back.
I don't recall exactly what the structure is. It writes it onto the disk. It's an asynchronous call. You can make it async, and then so the Lambda just runs, says async, and then it happens, and it writes to S3.
It drops all the segment files onto disk, and then when you call a restore, it will recreate the collection from the index.
Okay,
So you'll have a fully searchable collection when you call the restore operation.
You just have to get it back out of S3
Right.
onto the.
And it's the same method for getting it out of S3. It comes right through the file gateway.
Because a new node launches, that volume is mounted, and all the backups are available on that mounted path.
And it just has to come back.
Yep. That backup does also include the ZooKeeper information, so that configuration we did not have to treat separately.
Do you find it easier to use the file gateway than just like doing S3 copy?
We tried using the S3 copy command. We also tried writing a library that hooks into Solr that writes it directly to S3. We had little success with that, and with S3 copy, you can't do that because the backup API requires a shared file system. It will return a 400 if you don't include a shared file system path.
When we were originally targeting Fargate with the thought that we could use HDFS to write to S3 URLs, but we couldn't make that work. At one point, we were actually debugging Solr's code base and a container running in Fargate from IntelliJ on our desktops to try to make that work, but we ended up having to kick that can and put it back on ECS. But yeah, EC2 instances, so that we could mount the shared file system. All right, so I want to talk a little bit about some of the issues that we had, and I found this image which I thought was pretty incredible. But one of the initial problems we had with our architecture was that the way we defined our health checks was rather simplistic, and when one of them would fail, it turned out a lot of them would fail. So like originally our ECS container task health check was just making a request to like the Solr API, like /Solr/, and if that got like a 200 to 399, it was saying it's good. But when we had some garbage collection pauses, or like we blew heap or had a ZooKeeper issue, they would all fail, and it would just start killing tasks more quickly than we could auto heal.
And it was pretty aggressive with killing them. After maybe 2 failed health checks, 5 seconds apart, ECS would automatically kill that task. And then what would happen is you'd get some sort of cascading failure where you lose more nodes than you normally would have in a failure scenario.
So for us, we really have an opportunity to look at how we built the health check to make it more accurate and robust. Like, what does it mean for a collection to be healthy for us? We have all the replicas of the shards that we expect to have. We haven't done that yet. In the short term, we've made those health checks less aggressive, so they're not killing things as quickly, but that limits our ability to auto heal quickly. Another issue is, since we're not doing our chaos testing in production, it actually covered up an issue that we had with disk growth. So when we deployed ZooKeeper, we were not expecting much data on the disks at all, and we neglected to put any kind of disk check in. Well, our disks filled up, and what we found out happened was that ZooKeeper, at least in the Docker image, by default will take snapshots of your data, but it does not auto-purge by default. So it just, over the course of 9 months, ended up filling our arguably small disks, and we had a ZooKeeper outage.
And obviously that happened during the most busy part of the day for us.
Only in production.
Yeah.
With our chaos testing in QA, killing tasks, we never hit it because we got a fresh disk every so often.
Just real quick.
Yeah.
How long did it take ZooKeeper to hit your disk limit? A couple months?
9 months.
9 months.
I think it was 9 months.
Yeah, sounds about right.
And we might have had releases in the meantime, in there at some point that killed things, and because when we deploy new,
we cycle the cluster every once in a while where we just kill off every task, wait for it to come.
So probably less than 9 months, but 9 months is when it hit production.
Yeah.
Right.
There is an auto-scaling bug that had a JIRA opened up and was closed. That's in 2 minor revs or patch revs past where we are right now. And it's based on our use of basic authentication in our cluster. So what happens is those auto-scaling node added, no lost events fire, but then something in the cluster communication, I think, is trying to authenticate and it fails. We need to simply upgrade our Solr version. I think we're on 7.5.1 right now. And it's like 7.5.3 or .5 or something that fixes this. So that's actually impactful to our production environment, but not into our dev and QA right now. If anyone has any more information on how we could maybe work around that, I would love to hear it. But our plan right now is to simply upgrade and hope that that takes care of it. And then like we talked about with Fargate, we had the backups required that shared file system, and Fargate didn't have support for that, so we ended up having to build instances and run ECS on EC2. If at some point Fargate does support shared file systems, Amazon has another product called EFS, Elastic File Service. If it supports one of those, we may look at bouncing back, but it's unlikely if that would get prioritized. And then our business is just simply immature at data capacity planning. And it's something that we know, and we have some things outlined to hopefully make it better. But just a couple of weeks ago, we had to shut down one of our development teams that was about to onboard millions of new catalogs that would have inflated our product index size to the point where we probably would have started blowing heap. And we ended up doing some things. That's what led to us sharding the products initially.
Relieving some memory pressure from.
Yeah, so we're lucky we got ahead of it before they just loaded all of the information and then it ended up indexing. But data capacity planning is definitely important, at least until you have the ability to auto scale outward, which is something we thought we could wire up, but we have not gotten around to either.
I think that just about covers it.
We have some time for questions, like
10 minutes worth of questions.
Awesome. Yeah.
Yeah. So you're pushing. You have an overnight job that puts data into Solr. Do you have any changes that happen between those jobs?
Yes.
Yeah. Do those go straight to the kind of currently live?
Yeah, it's our products collection that has the complicated ingest from different suppliers and different ways that we receive information. For order history, that's just an update document back to the SolrCloud. Invoices as well.
So those changes would get persisted through the backup in the following backup run.
Yes.
Correct.
But your backups are like downstream of Solr. Did you consider using data import handler with a database ahead of Solr that you pull changes from, so that Solr is just a copy?
That is how we ingest products. It comes from a database, but the ways the data gets into that database are vast. And so intercepting every type of update to that SQL database, we have several of them already doing near real-time updates, but just in case there are some paths that are missed, and we do that full reindex every night just to account for those.
Transformation process from those databases to what you actually want to put into Solr is really complex.
Yeah. Oh yeah.
It's a pretty intense SQL Server stored procedure.
That's actually the main thing limiting our reindex time is how long it takes us to start getting rows out of the database.
You're using something that pushes Solr to Solr.
As well, yes. Yep, we've got a messaging system as well. So we can publish a document, and we have a subscriber to that will write it directly into Solr for our real-time updates.
Actually,
Yep.
I think you were first.
Yeah. How do you reconcile the SolrCloud, auto scaling stuff with ECS's auto scaling?
At the moment, we have a fixed ECS cluster size. So we have grown it as we've needed to, but we're not scaling so dynamically that we need to go up and down. What we do, though, is when we do a deployment, we want to do like a rolling update of the cluster. So what happens is, you can probably speak to this a little bit better, but we'll get a new task definition, and then ECS will start killing tasks or instances one at a time, and we wait for it to become healthy.
I'm actually going to rewind here really quick to show that really quick.
Like if you said 2 shards and 5 replicas, right?
Yep.
And so how does ECS know you lost something out of shard 1 versus shard 2, or do you not produce it?
ECS is agnostic to that.
Okay.
So ECS is just in charge of spinning up the images
Yep.
and the containers.
Yep.
And then Solar, we have to use some tooling to, know what replica went missing so it can add it back. And
So Solar's
has most of
auto
that
scaling
built in.
handles that.
Right. I was wondering how you married the two together. It sounds like you get notification that.
Yeah, and if we were to add another ECS node, just go from 15 to 16 or 20 to 21, that node added trigger would fire, and it would take corrective action if it needed to.
Okay.
So that includes rebalancing replicas to different nodes and all that kind of stuff. I want to rewind to this though really quick here and talk about that rolling upgrade again. So that Solar min healthy %, that's saying we want to keep at least 93% of the cluster alive when we do an upgrade. So when we push out a new ECS deployment, it's only going to kill 7% of the tasks. And in a 15 node cluster, that's one task at a time. I think. Something like that.
Yeah.
The number in our production deployment might be different than what's on the slide.
I was curious about where is the data stored on the ECS. So we use bare metal machines with locally attached disks. So this is quite interesting, something we want to think about. Where is the data stored? You talked a little bit about the snapshot persistence, but on the live node, where is the data being stored?
It's not. It's just on the file system of the Docker image.
It's the root volume.
The root volume, right?
Whatever the volume, that's what the root volume size, 100 gigs there.
So the root volume of the root EBS
And
that
kind of
gets
follow-up
attached.
question to that. So what happens when an instance is killed and it has to do replication? Have you seen any? I assume like you were mentioning the data size was 12 gigabytes, right? The index size. So probably full replication is quite quick when a new node comes up.
Yeah, and that's something that we try to avoid during the day, just because it does add load to the cluster to have to replicate 12 gigs of data over the wire to a new node. So it's something that's possible, but we try to avoid it during business hours so it doesn't impact anything just in case.
When we have seen it, copy that, less than a minute for the new one to become healthy and green.
It's fast in AWS.
Yeah.
For the backups, I think you said you had an NFS mount, which is internally backed by S3, et cetera.
Correct.
How did that NFS mount work with Kubernetes? Like, how did you articulate that mount?
Well, so we didn't use Kubernetes, so we're just using ECS. And in the ECS container definition, so we mount it to the EC2 instance and like the user data of the EC2 instance. And then the container image says mount this path in the Docker image or in the Docker container to this path on the instance.
Yeah, this right here, this file share ARN is used in the user data script for each of the instances that launches.
I think
What did he say?
so the question was why ECS and why ECS instead of EKS? So why ECS instead of Kubernetes? And I think it just comes down to we had more experience with ECS at the time.
Our organization is just getting started with containerization as well. So diving into something like Kubernetes for this wasn't what I'm about to say initial experiments. This wasn't an initial experiment. We started with some low risk web apps and web services beforehand, but jumping into something like Kubernetes off the bat would have been a huge undertaking. And our organization is actually moving towards HashiCorp's Nomad product as a container orchestration instead of Kubernetes, just because we are integrated with a lot of the other HashiCorp tools right now. Like we use Terraform for infrastructure, Packer for building images, and even Docker containers provisioned with Chef. And then we have their product Vault deployed for secrets management. So Nomad and the other piece that comes with it, Consul, kind of complete that collection of services rather than plugging in something new. We would then have to either replace stuff that we've already got running. It's just not going to work as well. So we're moving towards Nomad.
And you get rid of ECS. Get rid of ECS.
We will likely migrate some systems that we have on ECS into Nomad. Yes.
Ultimately, the plan would be to have all of our software, including Solar, running as a service within Nomad. But that's in very early stages. We might have time for one more. Oh, I think we're done.
We're done? All right. We'll hang out in the hallway, though,
Yeah,
for
feel
anyone
free to
else who
come
wants to
after.
ask a question.
Thank you.
Thank you.